Good evening, everyone. Welcome to the first session of the Waterloo Data Science and Data Engineering Meetup event. We are in a virtual format for 2021 just because of the pandemic. And today we'll be talking about Q mining. We have Professor Arik Senderovich, who is an assistant professor at the University of Toronto. Professor Arik Senderovich has a PhD in data science and an MSc degree in statistics and a BSc in industrial engineering. These degrees were obtained from Technion, the Israel Institute of Technology. In addition to his educational qualifications, he has also received the Lyon-Sachs Scholarship and has previously worked as a postdoctoral fellow in the Toronto Intelligent Data Decision Engineering Laboratory. Professor Arik's interest lies at the intersection of operations management, data science, and artificial intelligence. He is involved in developing methodologies for automatically determining learning models for complex and congested environments. He has received a number of acknowledgements and accolades in the research that he has done. So without much more ado, I'd like to introduce Professor Arik to everyone.
Hello, everyone, and thank you, Zia, for the kind introduction. Let's get onto it. Zia, can you see my slides? So today we will talk about Q mining, which is a technique or a set of techniques to do predictive and prescriptive analytics in congested systems. Now you see the word health here because essentially all of my examples today are going to be from congested health systems, which is, I think, very relevant to the world we live in today. It is a great pleasure to be here. And again, thank you, Zia, for inviting me. Zia went through most of my bio. I'll just add and say that today I'm an assistant professor at the Faculty of Information here at the University of Toronto. And I'm also the scientific advisor for a cool startup company called Mindsy, a company that does process optimization simplified. So putting some of the theories we develop and algorithms we develop essentially into practice. So the main research area where Q mining was established is called process mining. For those of you who don't know process mining, we start with processes that are the backbone of any organization. We look at service processes, manufacturing processes. Now, in today's world, all these processes are managed, controlled by a process-aware information system. This is the assumption in process mining. And these systems create what we call event logs that can then be mined to extract useful information. So process mining is this combination of process modeling and data mining that is supposed to yield value to organizations. And the main goal of process mining is to, in a data-driven fashion, improve and analyze business processes. What do I mean when I say event logs? What do I mean by that? So events are essentially produced by the system. We have a sequence of activities here: register request, examine thoroughly, check ticket, decide, and so on. They're attributed to a certain case. That could be your loan application, that can be your visit to a hospital. And these activities are time-stamped, and there are resources and costs associated to them. So if you're coming from databases, this is what we call sequence databases or transactional logs. So depending on the community you're coming from, these concepts are have different names, but that's the kind of data we're going to consider in our analysis. So I like to think of process mining as this fusion of fields that brings in, I would say, theory from information systems, process and operations management, so managing processes and optimizing them. And the important component here is, of course, data. Everything should be based on data, empirical and evidence-based. So I think of process mining as this nice, neat, new combination of these three areas. And essentially, Q mining was born in this world of process mining, where my interests between queuing theory or operations management and data science came to life. So Q mining was the area of the main topic of my PhD. So in today's talk, I will talk about Q mining. I will give some introduction, motivation, and so on. I will give you some background what Q mining is about. Then I will give examples of Q mining in predictive analytics, specifically in healthcare applications. And then I will talk a bit about ongoing work in prescriptive analytics. So that's kind of the next step in the evolution of Q mining. And I will conclude with opportunities and challenges that are still open in Q mining, and I will open the floor to questions and a discussion. So that's the plan for today. And the motivation for Q mining comes from congested health systems. We wish that our health systems would look like this, not a lot of queuing going on, not a lot of congestion. However, unfortunately, sometimes our health systems look as follows. This is a packed emergency department in Israel, actually, where I come from. And this is an even longer line or a more packed situation. This is a line for an emergency department in China, where people are trying to get in to get service. And this is not during COVID. So this was taken before COVID time. So in these systems, we have three, I would say, families of analysis that we wish to conduct. First of all, we want to understand where our bottlenecks are and what is driving down our performance. So what is causing congestion? Where can we improve in terms of waiting times and so on? We'll call that bucket of measures descriptive analytics. That's not going to be the focus of today's talk. Then we have predictive analytics. We want to be able to predict when things are going to happen. So if it's a hospital, we want to predict when will it be that I will see the physician I'm waiting for. And this strongly correlates to quality of service, to the performance of the system, and so on. So it's known that predicting the outcome for a patient, how long they're going to wait, where are they going to end up, is strongly correlated with the experience of the service experience. So essentially, that correlates to anxiety. It reduces anxiety in patients and in customers in general, and produces value. Lastly, prescriptive analytics is where we want to make decisions, where we want to optimize and improve the process. Here, I'm giving the example of reducing ambulance diversions. Ambulance diversions is a phenomenon that happens when the ambulance is about to go to the closest hospital to the patient's home, but they're being told that the hospital is fully packed and they need to reroute to a farther away hospital. Now, this, of course, causes delay of care, and this may have critical implications on the patient's well-being. So when analyzing congested systems, those are the three buckets of analytics that we wish to consider. And here's an example for descriptive analytics at its best. This is applying process mining techniques, Q mining techniques, to a real hospital. So this is data coming from May 2014. This is real time. So this is real data, real event log being replayed over a process model or a process map. We see that patients arrive in the morning. They start with the lab. They wait to get into the lab. They perform certain activities in the lab. They go to vitals, and then they go into examination and chemotherapy infusion. This is data that comes from a cancer hospital in Boston. And actually, in this data set, we track patients at the level of 3 seconds, at every 3 seconds. So the data comes in a 3-second resolution. We know where every patient is. And then there's a non-trivial task of matching what the patient is doing to their location, because the data only includes location, but that's kind of a separate story here. But suppose that we got to data that actually describes the activities and the different stations that the patient visits. This shows a picture of where my bottlenecks are, and you can see that in the morning, my bottleneck is mostly the lab. Then closer to noon, it's the exam room, and then in the afternoon, the patients go through chemotherapy infusion, and the bottleneck or the congestion starts building up in that last part of the process around the infusion area. So that's what I refer to in terms of descriptive analytics. In terms of predictive analytics, we wish to typically, in these congested systems, we wish to predict the time until a certain event happens. When will the patient be seen by the doctor for the first time? It's a very important performance measure that measures success of emergency departments. When will the patient be released from the hospital, right? Because this is very important information for family members that will come pick the patient up. So that's predictive analytics, and that's going to be the majority of my focus today. Lastly, we have prescriptive analytics, as we discussed. How do we prioritize patients? Do they go urgency first? Do we want to do first come, first serve to accommodate fairness? When do we speed some patients up? Which groups of patients do we speed up? all sorts of routing and staffing decisions. How many nurses will I require? Where should the next ambulance go? And so on and so forth. So that's prescriptive analytics. And that's going to be the last part of my talk. Now, Q mining is based on the assumption, again, that everything that is performed in the healthcare system that we're analyzing is logged, or at least enough is logged such that we can actually bring value using Q mining for the organization. And so the idea is to try and discover queuing models that come from queuing theory, which is a field in operations management. And once I've discovered the model, I can do descriptive analytics, I can do predictive analytics, and I can do prescriptive analytics. Okay, so that's the main pipeline of Q mining, starting from the process, analyzing the data, and then analyzing, essentially having the model out and using the model to give better predictions and better prescriptions. Now, before the PhD, at the time Q mining was born, in process mining, the methods did not actually consider multi-case perspectives when doing, for example, predictive analytics. They were mainly focusing on a single case view. We would look at a single loan and try to use its characteristics to predict when this loan is going to be finished. However, all the loans are flowing through the same set of resources, and therefore, if currently all my administrators are busy with other loans, my loan is going to be delayed. This was a realization that Q mining brought into process mining. On the other hand, in queuing theory, there was a lot of, as its name implies, there was a lot of theory that was created, but not a lot of it was tested on real-world data. And queuing theory is theory of small models, of simple, robust models, and it wasn't clear that they can be applied to big data, right? To huge settings where we have all these details, and emergency department is not a simple two-station process. And so here there was a kind of a contribution to each of the fields. In queuing theory, we tried some of these methods empirically on real-world data sets. And in process mining, we introduced the notion of queues, congestion, and multi-case perspective when analyzing the processes. So that's how Q mining came to be. Now, a word on queuing models. What are queuing models? Queuing models are declarative models of the reality of the process. They're denoted by this, it's called the Kendall notation in queuing theory, A, B, C, Y, Z plus X. A corresponds to arrivals. So essentially, it's a declarative model, and we declare that our arrivals are completely random. And then this means that the arrival process adheres to a Poisson process. Similarly, we can say that all my patients arrive at certain appointment times, so my arrival process will be appointment-based. The B component corresponds to service times, so we can assume that service times are exponential, and then the mathematical analysis becomes nice and neat. On the other hand, reality shows that oftentimes service times do not adhere to exponential durations. Things in life are not memoryless, and actually we find out that a lot of the times the durations are, for example, log normal or adhere to other distributions. Then we have the server capacity. So basically, when we will do Q mining, we will need to learn all these components. We will need to learn what is the server capacity. How many nurses do we have? Do their shifts change over time? Then Y corresponds to the Q capacity. Can we let everybody in, or do we have a limited waiting area where we cannot have more than K people waiting? Now, this is especially relevant for COVID. Now, many hospitals restrict the number of patients that can enter, and some patients are not allowed to come too early before their appointment time. I'm talking about outpatient clinics. Finally, we have Z and X. So Z corresponds to the service policy. What is the service policy? And there are works that try to learn what the service policy that the organization is now applying. Is it first come, first served? Is it processor sharing? And so on. And X corresponds to impatience. So this is especially relevant in systems where customers can leave. And you would be surprised to see, we're now working with a hospital here in Toronto, how many patients are actually left without being seen or left against medical advice. So this impatience of patients or of customers needs to be taken into account. And finally, if we have many stations like that, this is a single station, but when we have many stations, this becomes a queuing network, and then we can add the letter R to describe the routing scheme in these networks. The simplest model that you may have heard in the past is MM1. What is MM1? When A is replaced with M, it means that the arrivals are Poisson. When the B replaced with M, it means that the service times are exponentially distributed, and there's a single server, a single nurse, or a single doctor. Think of a very simple case where you have a clinic with a single doctor that sees patients. Now we're dropping here the Y, the Z, and the X because we're assuming that there is no abandonments in that system. There's no capacity to how many can wait in queue, and the service policy is first come, first served. So we have a fare-driven policy, first come, first served. And this model is very simple to analyze. There's a very fundamental and basic mathematical results that help us analyzing this model. For example, if a patient arrives and sees 5 patients in front of them, waiting for the doctor, there is an exact result to the distribution of the waiting time. We can say, and then we can say, what is the expected wait? What is the variance? We can give a prediction. We can give confidence intervals based on this simple model. But of course, in real life, systems are rarely MM1, and therefore we need this more general notation. And basically, the idea in queue mining, one of the ideas in queue mining is to try and learn the queuing model or the queuing network from the data. And then once you have the network, as I said before, you can start doing some analytics, some simulation, depending on how complex the model is. So for complex models, we cannot usually have the nice math associated with the MM1 model. So we will have to go around and use simulation. We will not have mathematical expressions to help us predicting the waiting times and so on. So how does queue mining work? We start with the data, and then the queue mining algorithm will learn all those components, the A, B, C, Y, Z, if you wish, that are associated with the data, right, that we find in the data. So we want to learn the routing between the different stations. We want to learn the dynamics. How do the arrivals behave? Do they actually adhere to a Poisson process where everything is assumed to be, the arrivals are assumed to be at random? What are the scheduling policies? And behind every line here, there's more or less a paper that describes how this can be done. For example, learning scheduling policies is something that can be turned into a classification problem, and then machine learning techniques can be applied. So assuming that you've learned your building blocks, what you can do next is to either use closed form mathematical expressions like we did with the MM1 before, like I told you about the MM1 before, or if the model is too complex, we can do simulation. So bring the system up to speed with 10 a.m. in the morning in our emergency department. This is how many patients we have. And now we can play the simulator forward and try to do that 300 times and predict how long will a patient that arrived at 10 a.m. actually wait. And the third alternative, which I'm going to talk about soon in the next couple of slides, is using machine learning. So how does knowing that there's a queuing model that is a good representative queuing model, how can this help us build better machine learning models, right? So we have a queuing model that helps us in constructing better machine learning models, and we will basically do that through feature engineering. So this was an introduction to queue mining, and now let's see how queue mining can help us in a predictive setting. So how does predictive analytics work? Again, we start with the congested systems system. We have raw data that the system generates. Let's say these are transactions, everything that the patient is going through while they're visiting the hospital. So I would say the green path here that goes from left to right is to turn this raw data, that is a sequential data or sequential database, into training data, as you would imagine in any supervised learning setting. And then use out-of-the-box machine learning model, whatever you choose. It can be random forest, gradient boosting, and so on. Now, this green path is what was happening in the process mining field before queue mining. So basically, congestion or this dependency between the different customers, patients, cases, the most general word would be cases. The interaction between them would not be captured. And basically the instance itself, so if this is my loan application, so my features would be encoded and used. So if I so far did A and B and C, that historical information would be encoded. But the fact that I am competing over the same resources with 5 other loan applications would not be taken into account. So when we introduce queue mining, we introduce 2 additional paths. So the first path we call it the, let's say, the model-based or the queuing model path. What it says is as follows: fit a queuing model based on the data, and then once you have the queuing model, the math or the simulation or simulating that model would tell you what the outcome is going to be, right? So don't use machine learning, use the queuing model that you have. Now, of course, the queuing model is always a very simplistic representation, and then it suffers from the problem of underfitting. These models are usually much simpler than the reality, and usually cannot capture all the complexities as well as a neural network would, for example. Now, the second path of process mining, and I want you to remember these two paths, path 1 and path 2. Path 2 is essentially telling you this: you know the queuing model. Now come up with a way to encode the information that you extracted onto the queuing model and the fact that you know queuing theory. How can you create better features that would capture congestion, add that to the training data, and improve the performance of your machine learning model? Right. So that's kind of approach number 2, and that's going to be the focus of what I'm going to present next. So path 1, as I said, let's call it simulation mining, because for realistic purposes, it's seldom that you can actually find a system that is so simple that it can be tracked and analyzed using the math results. So let's say we discover this complex system, like in this Boston hospital here, and we're simulating it. We're simulating the time until the patient leaves. We do it 300 times. We build confidence intervals in our prediction. And this approach works. We have a paper on it, and there's an earlier paper that does a similar thing without considering some of the queuing, without considering some of the queuing nuances. However, this system assumes knowledge of the resources. This approach assumes knowledge of resources and queuing events and how my system works exactly. So in a more recent work, we said, what if we want to use the power of machine learning to complement that knowledge? What if we don't assume to have that knowledge? We won't be able to differentiate exactly what is queuing, what is service, and so on. Can we feed it with enough information so that I can improve the performance of my predictions? And so I would say that path 2 here would be, let's try and come up with a good model, good representation to construct features for our supervised learning method. And we'll let it compete against another. So one example for that, before that work, was to say, okay, let's mine a basic queuing model, and let's build a boosting ensemble on top of that model that would use that model as a warm start. Okay, so that was the state-of-the-art approach before the paper I'm going to present now. However, again, this approach called the snapshot here, because it's based on a theoretical result in queuing called the snapshot prediction, it requires a lot of assumptions on the data and the process. It requires all that knowledge that I described. Even though we're using machine learning here, we're still not there in terms of assuming less knowledge, assuming less things on the data. So in this 2019 work, we actually introduced congestion graphs, which are more abstract than a typical queuing model that I've shown you, because they do not assume to know where the queues are, where the services are, what exactly the arrival process looks like, and so on. So it's a more general model. It is related to a general model in queuing theory, but you don't require as much expert knowledge as this model I've introduced before. So basically here we would require to know something about the system, and based on that, we would construct this ensemble of trees, of this boosting ensemble. So the way congestion graphs work, and this is the work that was published, this is the paper that was published in AAAI 2019, jointly with Chris Beck, my postdoc supervisor, Matthias Weidlich, a colleague, and Avigdor Gal, who is my PhD supervisor, one of my PhD supervisors. Basically, we take an event log, we create these congestion graphs that I'm going to show in the next few slides, and we use congestion graphs to extract features. Basically, we're following path number 2 in the predictive queue mining approach that I talked about earlier. So how does a congestion graph look like? Its structure is very simple. So these are dynamic graphs, but dynamic in what sense? They have a fixed structure, right? They have a fixed set of vertices and edges, but they have a dynamic annotation or labeling of their vertices. So the vertices are dynamic, have a dynamically updated component to them, and I'm going to show you what I mean. So the structure is very straightforward. Vertices are all the events I have in the log, and I don't assume to know the difference between a queuing event, a service event, and so on. So I cannot actually build a nice queuing model like I did before, but that's also the power of this approach. The edges between pairs of vertices are such that if I see a pair of events occurring one after the other for a certain case, for a certain application loan or a patient, I will draw an edge. But the edges are less important here. What is important is the dynamics. So the structure is very easily obtained. We have a patient 111 in the hospital that goes through 3 events, 1, 3, and 7. Event 1 is reception, event 3 is triage, and event 7 is treatment. So we add the edges. We say that 1 is a starting event, and we denote it with this arrow, and then 3 is the triage, and 7 is the treatment. Then the second patient, 222, has only triage and discharge. So that contributes the fact that there's an edge going from 3 to 22. Now, the vertices, we have from this log, we get 4 vertices, and we get 1, 2, 3 edges. Okay, so that's the easy part, the structure. What is the dynamic part? The dynamic part should capture exactly what I've shown you in that animation in the beginning. Where are the bottlenecks? Where are the entities that are waiting longer? So imagine that I'm going to update my my labels on these vertices every 5 minutes with crucial information about the congestion of the system in the past 5 minutes. Let's see how this works. And congestion graphs are coming. The intuition and the motivation came from these graphs I've shown you before. Basically, what we're going to do is we're going to add dynamic labels to our vertices, as I said, and those are going to be then mapped into congestion features. So this is the important part for the feature extraction, and congestion graphs are actually related to a family of queuing models called generalized Jackson networks. They're very general. If you remember the slash notation, the A/B/C, they are G/G, so they're general. We're not assuming a lot of assumptions here on the distribution of service times, arrival rates, and so on. So how do I proceed and how do I label the vertices? So very intuitively, the first thing we add to a vertex label, and it's going to be a triplet, so we're going to add 3 things. The first thing is the number of patients on the outgoing flows of that vertex. Right? So currently, there are 14 patients flowing out of waiting lab. This means that waiting lab has now more patients, for example, than vital signs. Right? This is an indicator that most of the congestion is now happening in the beginning of the process. Let's say that this is 9 a.m. in the morning, okay? The second component is how long these 14 patients are already spending on those arcs, right? So they're now traveling to their next destination, let's say lab. How long have they been there? And the assumption here, the longer they're there, the higher the congestion at this very moment. So a patient that would now arrive into the hospital would be expected to be stuck longer in that station. And the third component is the vertex inter-visit time. How often is this vertex visited? And this corresponds somehow to the arrival rate, to the arrival process into the vertex. And I do it for each and every vertex. So at each point in time, every time that something changes in the system, imagine my system running over time, I'm going to update the labels of those vertices. And I'm going to do it dynamically as a function of time. And we show that these 3 measures are actually approximating the Markovian state representation of the corresponding generalized Jackson network. So what happens here is that I'm going to add the label 14, because we have 14 customers waiting, 60 minutes, that's their total time spent so far in the waiting state. And 5 minutes is the time between 2 recent consecutive arrivals into waiting lab. So I'm going to take that triplet, and that's going to serve as part of my features that I'm going to feed into my machine learning model. And I'm going to do it for each of the vertices. So I'm doing it for waiting lab, and then I'll go to lab, and I will say, okay, here I have 18 people, but they're only then there totally for 10 minutes. And the arrival time into the lab is 10 minutes. So we have a less congested system, a less congested node on lab, because the inter-arrival time is smaller. The inter-arrival rate is smaller, and people spend less time in that station. So we get a long vector of these triplets, right? So what we get is the following picture. Suppose that we're now at 7:30 a.m. in the morning, and this patient experienced a reception end. And we want to predict when is this patient, when will their treatment end. Okay, so we want to predict that in 1 hour and 40 minutes, the treatment will end. What will we use as features? If you imagine that this is our training set, what will we use as features? We will use those numbers, those Markovian state representation vertex labels that we extracted from the congestion graph. We will say the first column, the first feature is going to be the number of people in lab weight, and that's 14 for that specific time. And the 60 minutes and 5 minutes, and then for lab it's going to be 6 people, 35 minutes, and the rate is and the inter-arrival time is 15. And we're going to do it for every row in our training data. Now this is information that is available in real time. When this patient arrives and does a reception, we can actually, our information system can be set such that this is computed in real time. So we're not using any future information here. This is everything that happened up to that moment. That's, let's say, the most recent update that we got from our information system up to that moment. We're not using any information from the future, so we're not contaminating our training data, essentially. So this is how we build the features. And once we have the features, we know what to do. We go and apply our favorite supervised learning technique, right? For example, here in this paper, we use several, but the best technique that worked best for us was XGBoost. So how does this work? We take a training log, as I said before, that hospital log. We turn it into training data using congestion graphs. And then this training data gets, we feed it into XGBoost. We train a model, and then when test data comes in, we can still extract those queuing features from the test data because everything is available to us in real time. We don't need to, everything is causal. And then we can feed the new input into the model and get a prediction. Yeah, so this patient is going to leave at 9:10. Okay, so hopefully if our prediction is accurate, this is the result we're going to get. So that's the experiment. That's kind of how this will work, and that's the experiment that we ran. We actually used it on more than one data set, but I'm going to, and shown the value of the approach, but I'm going to show you the results for only one data set, also because of time considerations. So the data set is that Boston hospital I told you about before. It's called the Dana-Farber Cancer Institute. It's one of the top 3 cancer institutes in the East Coast of the United States. And the time period that we considered was April to December 2014. We had 240,000 events to be aggregated into an event log. And the prediction query was, given that I now arrive to the hospital, how long will I stay there? When will my family members need to come and pick me up? And we had the following experimental setting. So we had 4 scenarios. The first scenario was we wanted to minimize concept drift or minimize interference of all kinds of seasonal effects. So we took 1 month of training, April, and we tested it on 1 month of on May, basically. Then we had a summer setting where we did April to August as training data and September as test data, April, May, June, July, so till July, and then we tested it on August, and hence the summer. And then in the third scenario, we did in the entire 2014. Right? We took 7 months of training, the last 2 months for test, and we tested how robust this approach is, because in the winter, as we know, healthcare systems change, especially in the other data set we had that comes from an emergency department, right? Because the winter in the emergency department, as you can see around here, even with COVID now, we see that viruses, the flu and COVID, they prefer the winter, and we have packed emergency departments in the winter. So we wanted to check how robust this approach is. If I train it on non-winter months, will it perform well in the winter? And the last scenario was the high load scenario, because we know that queuing theory, a lot of the assumptions there hold in high load. We took the summer setting, but we only focused on the busy hours in the hospitals. And our baseline predictors were long-term average. So this is a very naive prediction. I arrive and I get the prediction of how long previous patients before me waited. I'm just averaging their waiting time or their length of stay, and I'm giving that as a prediction. The second one was a moving average of the last K patients, how long they've stayed. The third one was associated with the hour. So if I arrive at 9 a.m., it's different than if I would arrive at 9 p.m. So in the third prediction, we're taking this hourly context into account. And B4 was the best queuing-based prediction that I've already shown you, the one that uses a boosting ensemble and so on. So let's call it a snapshot predictor. That is based on things that were considered state-of-the-art before congestion graphs. And when we look at the results, these are the 4 scenarios: scenario 1, scenario 2, scenario 3, scenario 4. All we want to show here is that taking this Markov state representation, taking these congestion graphs into account, helps reducing the error. So this is not the smallest error that we got, in the sense that when we added clinical information, right? If we know that this patient is urgent and this patient is not, of course the prediction is going to improve. But in this experiment, we wanted only narrow down the effect of congestion. And we were able to see that we were able to show that there is an improvement. Otherwise, of course, our AAAI paper would not be published. We were able to show that there is an improvement here, and it was across several data sets and across several scenarios. And then we've also shown that when you bring in clinical information and additional information about the patient, you can do even better, right? So, and this approach was actually partially implemented in that hospital in Boston, I've told you, for predicting how long patients are going to wait for their blood work. So these were the results. Now, the nice thing about this congestion graph approach is that it also gives you some sort of explainability, right? Because if I use, for instance, random forests or XGBoost, I get the option to rank my features. I can run feature ranking. And in this model, every feature is essentially associated with a place in the process, right? So if I discover that a feature that has to do with order imaging test is the most influential feature, then your length of stay in the emergency department is mostly influenced by how long you're waiting for your images to arrive, right? You did your X-ray, how long are you waiting until that X-ray comes back? If this happens quickly, you will be out of the hospital quickly. Now, we did it in a static way. We kind of detected it independently of time in that paper, but there's a nice follow-up paper that was published in ICPM 2020, where the authors looked at dynamic bottlenecks. Like that example I gave you in the morning, we have more congestion happening in the lab. In the afternoon, we have more congestion happening in chemotherapy infusion. Right? So one nice thing about these queuing models and congestion graphs is that you can map the features back to the process and understand where the problematic parts are. So in a way, this already leads the way to prescriptive analytics. So that concludes the predictive analytics part. And now I will switch to talk for about 10-15 minutes about prescriptive analytics. So how can we use Q mining to do prescriptive analytics, improve the system, give better recommendations? And this is an ongoing work that I conduct with colleagues from the Rotman School of Management and others. So prescriptive analytics, we can still follow the same 2 paths as we did in predictive analytics. We can either create the model from the data and stop there and use simulation, right? And the extension we're working on is how do we handle this resource information that is often missing, right? We have data from a Toronto emergency department, but we don't know how many doctors and nurses were working at the same time, at that time. So in order to improve the system, it's very difficult to build a good model without having resource information, and that's the gap we're trying to overcome in the approach I'm going to show you. The second path I'm not going to get to today, maybe I will hint to it at the end, and that's using causal deep learning, essentially, to try and give recommendations, basically replacing parts of the simulator of the queuing model with black boxes that comprise neural networks. So, and how to do it in a way that is statistically sound. So the first path is about simulation mining. So a very similar approach. We mine a simulation model. We play this. We play the system out 300 times, and we change the number of nurses, and we see how this influences the system. Does it improve things? Does it make things worse? Now, there's a research question here. Can we relax again some of these knowledge assumptions? Can we assume that we don't know where the queues are and where the services are, just like we did with congestion graphs? And the answer is that yes, we can do that. And the way we do that is by building what we call infinite server models. we build models, queuing models, that are independent, kind of like our congestion graphs, independent of resource information, but we still bake in congestion or the resources in an indirect way. So instead of mining a model where we know the number of resources and we estimate it, we're going to mine a model that the service times are going, or the activity times are going to slow down as we have more and more and more patients. Very similarly to how we did in congestion graph mining. And for that, we developed actually a solution called the Q Miner. It's now going through all kinds of procedures to become a tool that we use with colleagues from Rotman. And here the input into the approach is this event data and some hyperparameters that the user can tune. And basically the tool learns the topology of the system or the structure, again, the arrival process, how the sojourn times behave, how the transition matrix behaves, and so on. So basically we're fitting the queuing model, and then we're spicing it up with arrival, predicting the arrivals using LSTMs and with all kinds of other cool features. And this model essentially will give recommendations for how many nurses, how many doctors one will need for each of the stations, which patients should I speed up and which I should not, and so on. And we, again, validated this approach or this tool, the QMiner, using real data. We tested it on 2 hospital data sets, one from Singapore and one from Israel, and 2 cloud computing data sets. We actually used the available data that comes from Azure and Google Borg, I think it was, to try the methods out. I'm going to show you the results for the Israeli hospitals. What we see here on the y-axis is the number of patients in the hospital. In blue, we have the actual number of patients. In red, we have the prescribed number of patients given that I'm going to change something in my system. Sorry, this is historical data. So this is to show you how well my model, the red model, captures the reality, okay? And the green is the confidence intervals. Of course, you cannot see anything here, but if you zoom in, you will see that the model replicates the reality in a fairly good fashion. Now, this is, of course, only step 1, because validating the model is a good step that we need to do, but the next step would be predicting unobserved behavior with this, right? So what we're working on now, let's leave out some of the data and see if the model still behaves in a good way. And then the third step would be giving recommendations and prescriptions using the model. So we see that for the total number of patients in the system, we're fairly within the confidence intervals. When we're going to specific activities, we see that in the upstream activities like reception, we're doing pretty well. But when we go down the stream and we have rare activities like the consultant activity here, our model starts averaging the noise and doesn't capture the variance well enough. So this is something that we are now improving. In terms of the results, so we have some optimistic results of doing Q mining for prescriptive analytics on 4 real-world data sets. In terms of future work, we want to extend the framework with additional features. There are some working papers that are coming out from this work. And of course, the hospital here in Toronto that we collaborate with, we want to try the methods that I've described before, both the prescriptive and the predictive methods, to see how that works on a live project where we have live data that gets refreshed. In terms of the second path, I'm just going to hint at it. Basically, the idea is this. So we get a simulation model from the data, but the issue is that some of these the simulation functions I need to code manually, right? I need to manage the queue. I need to decide that it's first. I need to mine and understand if this is first come, first served or not. But if it's not first come, first served, I need to write manual code that would say, okay, for queues that are last come, first served, this is how the queue needs to be managed. And the research question is, can we replace these chunks of code or these chunks of simulation code with machine learning models? And the answer is, and we have interesting results that show it, yes, and we can do it using causal machine learning. This is a joint work with Professor Ofer Baron from Rotman and Professor Mark van der Laan from Berkeley. This is actually a working paper. And with this, I would like to thank you. Here are my contact details. Feel free to contact me anytime to discuss. And I would like to kind of discuss these opportunities and challenges in queue mining, and maybe give some background to things that we can discuss here between us. There are issues of data quality. As I said, what happens if we're missing the resources? We need to have indirect methods to estimate things like resources and other components. The second thing is, it turns out that when we do queue mining, for example, using congestion graphs, we can actually reveal we can compromise patient privacy. So we've shown in a different work that you can actually extract patient priorities based on some of the decisions we're making along the way. So we have a paper now that we are submitting for each guy that talks exactly about these issues of how do I publish my event logs such that someone who is doing queue mining or other forms of data mining will not be able to extract patient priority or customer priority. More topics: prescriptive analytics with causal machine learning, I mentioned, and I'm also now working with a group from Rochester and Ben Gurion University in Israel on queues with invisible customers. So what happens if I arrive into Starbucks, I see the people in front of me, I have 3 people in front of me, but actually there are 5 other people who are doing mobile pickup. And I don't see them, but they're actually in queue. How do I then provide a good prediction for how long I'm going to wait? So that's what I had for today. Again, thank you, Zia, for having me. And I would be happy to take questions or discuss some of these topics to a deeper extent. And thanks everyone for joining. I'm not sure how many have joined, but thank you for joining.
We have quite a few people live watching us right now, and I have quite a few questions as well. So thanks, Arik. Let's go to some questions which have come up in the chat window. I'll pull them up one by one so you can go through them. Okay. The first question is, this was on slide 14. Why is C separate from Y? Are both capacities that change over time?
So these are 2 different things, right? So server capacity, imagine how many doctors I have, right? Y would be the queue capacity, how many chairs I have in my waiting room, right? So how many, what happens is that if you have a finite Y, let's say Y equals K, when the K plus 1 customer arrives and wants to join the queue, they will be blocked. They will not be allowed to enter the hospital. Effectively, this is like saying I have 100 ICU beds, and if the 101st patient arrives, I need to route them away from this hospital, right? For server capacity, this means that I have 3 doctors. I see the analogy here, but in queuing, we make the separation of waiting room capacity and server capacity. Together, they kind of comprise the overall capacity, right? But we make the separation, and both can be dynamic. So both can change over time.
Okay.
Very good question.
Then we have another question on slide 21.
Yeah.
So this was around feature extraction for both the methods. So could it be done using ensemble methods, by building ensemble methods, or something around congestion graphs?
Right. So the ensemble methods here, we're essentially we have one measure that is the snapshot prediction that comes from queuing theory, that comes from a queuing model that we assume in the system. And we don't extract it as a feature, we build the ensemble around it. So the way it's done is as follows. We take the prediction from the snapshot predictor, we look at the residual or the error, and we try to correct it using a decision tree. And then we take the error from these 2 and try to correct it with the 3rd decision tree. So this is very standard thing to do. This is how boosting works. But the nice thing is that the first predictor is not a tree, but rather is the snapshot predictor that comes from queuing theory. So the main approach here is not based on feature extraction. It's based, again, on this queuing model-based approach. We call it learner adaptation or learning adaptation. While the congestion graphs approach is actually based on feature engineering and feature extraction. I don't know if that answered the question.
I'm assuming it does. I think the question was how is feature extraction done? On slide 29,
29. Sorry, say again.
29.
Yeah. Yes, this slide. And what's the question?
So the question is, I didn't see any features for service capacity, like variables of the system. For example, how many nurses in night or day, etc. So there may be a hint of missing features when you extract features using your techniques.
Yeah, so that's exactly, it's a really good question, because that's exactly what we're trying to overcome, right? We don't have those features, and we're trying to indirectly approximate them by looking at other features that we hope essentially provide proxies to the number of nurses, doctors, and so on. Because we discovered, as we apply these techniques in many emergency departments, they usually don't have that resource information readily available, at least not all of them. And you need to try and approximate the congestion without knowing the staffing at different points in time. So that's a very good observation, and that's exactly what we're trying to resolve with this approach. Because if we would have the number of nurses and doctors, we could construct a reasonably good queuing model and use that.
Okay. There's another question. Is there any attempt to adopt max flow method algorithms or predictive analytics?
Not that I'm aware of. It doesn't mean that there are no such attempts. I'm just not aware of them.
Okay, we have another question. What feature ranking methods are used?
So we used whatever out-of-the-box XGBoost provides. I really cannot remember. These experiments we have ran them in 2018. I can send you the link to the paper. If you send me an email, I can send you the paper, and then you can look into the details. And I can look into the code. The code is also publicly available. So I just don't remember the exact techniques we used. Whatever is out of the box for XGBoost for feature ranking.
And is the code available on GitHub or some other place?
Yes. I gave the link. I don't know, Zia, will we publish the slides?
Yes, we can publish the slides.
Okay. Sounds good.
Okay. I don't know if this is a question or a comment. I'm working on my thesis to extract features from GTV to predict OS time. So was there a question around this, or this was just a general comment? If,
GTV?
Okay, there are no more comments at least, but I have one or two questions. So when you were doing data collection, what nature and form was data being collected? Was it just through logs, system logs that you had, or was there some manual tracking? Individuals were constantly tracking as individuals were moving around. Did you have concerns or questions from the hospital administrative staff around patient privacy?
So it's a huge question, very good question. So first of all, different hospitals, we have different granularities and different types of data, right? So the typical data you get in healthcare settings are those transactional logs collected by the information system, right? If you have an information system like Epic or other systems, basically the IT department writes a few SQL queries, and that's what they give you. The unique data set was indeed the one that you mentioned, Zia, the one that tracks patients every 3 seconds. So the hospital in Boston, when they've built their building for the outpatient clinic, they actually wired it with RTLS, and the patients are all signing a consent that they're willing to give their location every 3 seconds. They all wear badges. The doctors wear badges, the nurses wear badges. So there was some resistance in the beginning to wear these badges, but once this was overcome, they have no problem for the data to be collected. Now, when they started moving the data to us, of course, we went through the usual NDA proceedings, and there were experts that made sure that no private data is leaked. But I think that there are improvements that can be made there, because it's very hard to actually, in practice, make sure that no private data is collected. So we had other hospitals, other places we worked with where people were sending sensitive data over emails, right? So, but yeah, here in this hospital, it's very high tech, and there was a very I would say, very secure data transition. Things were anonymized, things were removed from the data. We get the data at the 3-second resolution, and then we start the aggregation process. So we actually get the track log. If I visited that hospital, I can actually see where I've been every 3 seconds. But I don't know who the patient is, right? The patient ID is completely anonymized.
And there's a follow-up question around patient privacy. I'll pull that up right now. It seems that the privacy concerns arise because the predictive analytics is not broad statement about the general hospital population, but about each individual's patient waiting time. So it's not a question, it's a comment that rather than looking at the general hospital performance, I believe it's considering whether certain patients, based on the nature of their treatment and the type of patient they are in terms of age groups, there is certain granularity in terms of feature extraction that would allow possible identification of patients. And that's probably the worry here.
Because we're interested in individual prediction, right? If we would be interested more in the descriptive analytics, like tracking down bottlenecks, we wouldn't even have to, we may even be, it would be sufficient to give us how many patients were in every station every 10 minutes or something, right?
Yeah.
We wouldn't even have to know individual characteristics. But since we're interested in doing very low level, very detailed individual predictions or prescription analytics, we do need to know these individual patient characteristics, right? What was the patient's triage priority? What was the patient's gender, age, and so on. So all this information is very useful to make predictions.
And I had one question as well. Is your work only relevant for large organizations which have considerable congestions? Or is this something that you could extrapolate in other domains as well? For example, the computer networks domain, because congestion, network traffic congestion, or for that matter, even going beyond computer networks, general traffic management, because roadways, motorways, highways, they have considerable congestion problems as well. And do you see this work being relevant and applicable to computer networks and general traffic management networks?
Right. Another great question. So the answer is yes. First of all, if there's no congestion, this method simply collapses to the previous methods existing prior to our work. When there is congestion, but it's not necessarily in healthcare, then yes, we've actually had success applying these methods in public transportation. So we had an European Union project with the city of Dublin, where we were making predictions for how long bus trips will take. And we used that snapshot approach I've shown with the ensemble was exactly from there. It's a 2015 paper where we're predicting traveling times, 2015 or 16. And then for computer systems, we are actually applying these techniques in a project, in the U of T project with Huawei. So we're actually taking the data sets from these organizations, cloud computing organizations, and using the simulator to give prescriptive analytics and to predict, for example, the number of jobs and virtual machines and so on. So this is broadly applicable. It's not only a healthcare, it's not only relevant in healthcare, and it's not only relevant in congested systems, but the benefit or the reward comes when the system has this queuing behavior.
Okay, that was fabulous. There are no further questions in the chat window, so I believe we've addressed all of the questions that the audience had. This was a great talk. The slides will be published, so keep an eye out on the description. I will update the description with the location of what the slides is. But Professor Arik, I really appreciate you coming over and having this session with us. The audience, I'm sure they learned quite a bit about Q mining. I know personally I learned quite a bit about Q mining as well. Thank you for your time.
Thanks, everyone. And thank you, Zia. Special thanks to Zia here. Yeah. Wonderful initiative, and thank you so much.
It's our pleasure. And thank you for the audience for joining us today. Please subscribe if you can. We just started our YouTube channel, so we could do with a few likes and a few subscriptions. But thank you everyone for joining us, and stay tuned for further sessions on data science and data engineering.
Thank you.